So, a very good afternoon to everyone. So, my topic for today's presentation is memory management and virtual memory in operating systems. Um, this is one of the most crucial components of any operating system, and understanding it helps us realize how computers efficiently handle multiple tasks. So, let's dive straight in it. This is RP Naveed. So, as I said, the presentation explores memory management and also the virtual memory concepts. So, let's begin with memory management. So, what is memory management? Alright, first off, it's very simple words. Memory management is how your computer operating system decides which app or program gets how much memory and when it should be free of memory. Imagine this, you open Chrome, a game, and a music player at the same time. If your OS doesn't manage memory properly, your computer will freeze or crash because it don't know how to distribute memory. So the operating system acts as a manager. It ensures that every process gets the required amount of memory, and when the app is closed, it releases the memory. So why is memory management important? So which means the role in system performance. So now you might wonder, well, without proper management of memory, your system would crash frequently, and also some process might not get enough memory while others get more than needed, so it will get us a waste and the some will not get even a appropriate memory. So worst case, there would be memory wastage, like we said. So to keep up our system running smoothly, the operating system does its job by carefully distributing memory to different applications. So it's the important in preventing memory leaks. So memory leaks occur when a program improperly manages and memory allocations, leaving memory inaccessible and reducing available resources. Good memory management practices prevent leaks, ensuring the memory is reclaimed effectively, which leads to more stable and efficient system. So let's go to memory hierarchy. So this is where it gets interesting. So the memory hierarchy. So the computer does not have a single type of memory. It actually has a hierarchy based on the speed and size. At the very top, we have registers. So they are very fastest memory but very small in size. So then comes cache memory and etc. So let's see about registers. So registers are the fastest type of memory. So it's located within the CPU, used to hold small amounts of data and instructions, so currently being processed. So the speed is crucial for efficient CPU operation, enabling quick access to frequently used values and commands. So it also has a cache memory and random access memory. So where cache memories might slightly slower but still super fast, and random access memory RAM comes next. Also, which is the main memory where most active applications run. And finally, we have a secondary storage in 2. So we'll also see about it. So like the cache memory is that it is a smaller and faster type of volatile memory. So the stores copies of frequently accessed data from main RAM. So the high speed access improves system performance by reducing the time it takes to retrieve the data from the slower RAM. So and different cache levels are there. So which is L1, L2, L3 serve to optimize the performance further. So what's the role of RAM into secondary storage? So as we have secondary storage like hard disk, SSDs and external drives which stores the data permanently, and RAMs are the which the main memory which is mostly the applications run in it. So they serve as the primary memory for a system, allowing for faster reading and writing of data which is temporary, and also but an active process it is. So next let's go to memory allocation. um so where the quantities of memory allocation are. So the first method is contiguous memory allocation. It means that when you open an app, the operating system gives it one continuous block of memory. For example, if you open a game, the OS might allocate a large chunk of memory. So without breaking it, it will give us a whole block. It is. So this method is simple but wasteful actually. So if there is a tiny gap in memory, it may not use it now. So causing the fragmentation. So contiguous allocation is fast but not very efficient. So the allocated and delocated memories are which can be wasted over time. So when there are contiguous memory, there are also non-contiguous memory allocation. So to overcome this problem, we have non-contiguous memory, which is to overcome the contiguous memory allocation. In here, instead of giving one large block, the OS splits the memory into smaller chunks and stores them wherever free space is available. Imagine you're filling water bottles from larger bucket instead of filling one big bottle. You fill multiple small ones and combine them later. That's exactly how non-contiguous allocation works. It's highly efficient and prevents memory wastage, but it requires complex management for operating system. So the paging in memory management and also advantages, both disadvantages in both methods. So in contiguous allocations, advantages include simplicity and speed of access. However, it suffers from fragmentation and limits in memory utilization. But in contiguous, non-contiguous memory allocation reduces fragmentation and allows for more efficient memory usage, but may introduce overhead from managing page tables and translating logical address. Segmentation can be more incentive for programmers, but paging necessities manage bits used in mapping logical to physical address, which can complicate system design. So going to virtual memory. What is virtual memory and what's the purpose? So now here's the magic trick, which is virtual memory. Suppose your computer has only 8 GB of RAM, but you're running multiple heavy applications like games, Photoshop, and Chrome. What happens when your RAM gets full? So this is where virtual memory comes in. The OS uses a part of your hard disk or SSD as extra memory. It temporarily moves some processes to the hard disk and brings them back when needed. This is why even if you don't have enough physical RAM, your computer still runs. And to move to demand paging mechanism. So demand paging is the method used in virtual memory. Instead of loading the entire program into memory, the OS loads only the required pages where the data is stored in pages. For example, if you open MS Word but you only use the file menu, the rest of the program stays on the hard disk until needed. So that's how the virtual memory works using demand paging mechanism. And there are also page replacement in it. For example, FIFO, LRU, and optimal algorithms. Page replacement algorithms determine how to replace pages in memory. So when a page fault occurs, so FIFO is nothing but first in first out, replaces the oldest page, and the optimal algorithm replaces the page that will not be used for longest time in the future. Each algorithm has different performance characteristics impacting the effectiveness of memory usage and system responsiveness. So, what are the advantages of FIFO and LRU and both the disadvantages too? FIFO is easy to implement but can lead to suboptimal performance as it goes not account for page usage patterns. LRU is more efficient in minimizing page faults by considering actual page usage. However, it requires more management. So, such as maintaining a list of page access times, both algorithms have trade offs that impact overall system performances. Depending on the specific workload and access patterns of the applications in use. So, what's the impact of replacement strategies on performance? So, the choice of page replacement strategy has significantly implications for system performances. Efficient page replacement minimizes page faults, resulting in smoother application performance and resources utilization. In contrast, poor choices can lead to excessive page swapping, reduced speed, and system trashing. Monitoring and analyzing memory usage patterns can guide the section of most effective page replacement algorithm for specific operating scenarios. So, in conclusion, effective memory management, including techniques like contiguous and non-contiguous allocation, um, virtual memory strategies, and efficient page replacement. We have also seen about memory management, how it handles the RAM usage, so how the virtual memory allows more processes to run. Page replacement also ensures memory doesn't overload. So the OS works smartly behind the scenes to give you a seamless experience. And that's it. Thank you so much for listening. I hope you have understood how your computer efficiently handles memory. So, do you have any questions? You can ask thoroughly.